So this is saying that there are different kinds of vector spaces. This was showing that there aren't two zeros. And this was showing matrices. Yeah, this was answers some of the true false questions. So are there any questions from the homework? Might as well go right to that. Any questions on the homework that I assigned? I'm not even sure what it is. Was it 1 through 4, something like that? Perhaps. Certainly 4A is here. Okay, let me see. I assume no questions is a good sign, I hope. I was able to look in the homework over the weekend. It was sort of odd. I didn't find anyone's because remember you received a message saying wait until Monday, I think. But then sometime over the weekend, I was able to find one student's homework submitted. And I didn't look very closely, but I didn't see their name on it. So be careful. If you submit homework, make sure your name at least appears at least once on it somewhere. If you didn't do that, try to submit again. Were you able to submit without the message again, or no? For those who recently tried. No, nothing. Well, I can't tell whether you actually tried or not, or if you had any luck
Well, I
or not.
submitted mine on Friday.
Okay.
Like when I finished everything that, like basically everything that we had covered.
Okay. Did you put your name on it? I hope.
Yeah, I did.
Okay, good.
Submit if we didn't put our names on it?
I'm sorry?
Do we have to resubmit if we didn't put our names on it?
I think so, because how would I know who did it? I mean, that's sort of self-evident, right? I mean, there are a lot of people submitting things. If you don't put your name on it, it could be anybody, right? So it should be submitted, I suppose.
Professor, I just wanted to make sure that it was due at midnight. Was it midnight?
I don't think that it had a date where you couldn't submit it past. So
Okay.
I hope not. I mean, if that's the situation, then I'm going to have to remedy that because I certainly want to let people turn it in later. I'm not trying to penalize you if you're late. So if it doesn't allow you because you're too late or something, then let me know. I'll let you know. Let me see what I've got. Maybe at the end of the day, I'll look at it again and see what it looks like. Let me add a page here. If I can. Good.
Are we going to be submitting weekly?
Yes, at the end of each week. Let me put some lines on this. Good enough. Okay, so let me turn to the book. So where are we? We're in section 2 on vector spaces. We talked about what it means to be a field. We talked about what it means to be a vector space and all the properties. We have represented different kinds of vector spaces. The vector spaces that you should be most comfortable with, I think, would be those from calculus. So things that look like R2 or R3, vectors in 2 or 3 dimensions. But we've talked a little bit about matrices and the notation for them, the row column notation. And those are vectors as well. And to be a vector space, with the takeaway, there's 2 takeaways. They're the detailed assumptions, which I think there were 10. In the book, there were 8 assumptions, but I added closure to the list. So there was actually 10 assumptions to be a vector space. And essentially 5 of them depended upon vector addition, and 5 of them depended upon scalar multiplication. You should know those conditions by heart. And you should also know them in a sort of general sense, in the way that I'm just describing them, that 5 of them depend on properties of vector addition. You could know them in terms of commutativity, associativity. So you can know them in a sort of general sense without writing the details down. And then also you should be able to verify whether something is a vector space or not. Some of the homework was along those lines. There are more properties here, but I think what I'd really like to do, there's a lot of homework here, a lot of homework, possible homework, I should say. I just assigned something like 1 through 4, but if you look in the text, there's much more. I may come back and assign some more of this as we go along. Let me see, maybe I'll do it now just to give you some other practice. Number 13 looks interesting. So I'll flip my mouse pad and my OneNote tablet around here. So for new homework for today, section 2, number 13. It's the exercises at the end of section 1.2. 19 looks like another one. So this is just verifying whether something is a vector space or not. I think for now that's good enough. So I'm going to move on into section 3. And section 3 is on subspaces. Okay, so it becomes a question, when you have a subset of a vector space, when is it a subspace? So let's answer that question. Suppose, let me look at the notation they're using. Suppose W is a subset of V, where V is a vector space. And this just means this is inclusion, or W is a subset of this. It might be equal to V. That would be sort of, so the picture would be this. If V would be everything in the Venn diagram, W could be a proper subset of it, something that looks like this. So then we would say W is a subset of V. So if you have a collection of vectors in a subset, where V is a vector space, when W is also a vector space, we say W is a subspace B. Okay. Well, let's do an example. The easiest examples again come from calculus. So let's suppose V looks like something that has coordinates V1 comma V2. And so this would be vectors in the plane. Vectors in R2. Okay, so suppose so I'm really saying that V is R2. And assume that. And suppose the set W just looks like the vector 1, 2. And let's actually put in a couple more vectors, 1, 2, -1, -2, and the vector 0, 0. So it's clearly W is a subset of V because each of these vectors are in V as well. But is W a vector space? VS is our abbreviation for vector space. Okay. What do you say? Well, what does it mean to be a vector space? I don't want you to give me the answer in detail, but give me the answer in general. What does it mean to be a vector space? Well, I'll answer it myself, but go ahead.
Sorry, I don't know, Mike. I don't know if I sound or not.
I'm sorry, your audio was muted. Try it, or sort of, yeah, a little fuzzy. Try it again. Now I hear nothing. Okay, I think someone was trying to answer. If you want to try again, go for it. Okay, hope your audio works better. When is a set a vector space? The answer would be if it has all those 10 properties we wrote down the other day, right? So let me answer my own question. When is W a vector space? That's question. Answer. When W satisfies the 10 properties from last time. And without listing them in detail, let me at least rattle them off like a grocery list. 5 of the properties have to do with vector addition. So whenever you add 2 vectors, you have to get a vector in the same space. If you add 2 vectors, they should satisfy commutative property. If you added 3 vectors, they should satisfy the associative property. There should be the 0 vector, and there should be inverses of each vector, additive inverses. Let me see, is that all 5? I think it may be. And the other 5 are what? Properties of scalar multiplication. So whenever you multiply a vector by a scalar, it should be in there. So there's closure. And what else? Some of the other properties there have to do with the distributive property of vector multiplication and so forth. So there's 10 properties you really need to check. Now, we could do all 10, but let's take a look in the book and give us a shortcut. So we look in the book. On page 17, they have this result in the middle of page 17. Fortunately, it is not necessary to verify all 10 vector space properties to prove that a subset is a subspace. And they say properties vector space 1, 2, 5, 6, 7, and 8 hold for all vectors in the vector space, and thus those properties automatically hold for any vectors in the subset. What are they saying? They're saying since W is a subset of V, and since if you add any 2 vectors together, the order doesn't matter, it wouldn't matter what if it. So for 2 vectors in W, it still would have the commutativity property, and it would still have the associative property. So many of the properties are inherited or just hold automatically because V itself is a vector space and W is a subset. Well, that reduces the work. So look a little further on page 17. Thus, with a subset W of V is a subspace if and only if the following 4 properties hold. What do you need? You need closure under addition, closure under scalar multiplication. The subset has to have the 0 vector, and every vector in W has an additive inverse. Okay, so there's only 4 properties we have to check. We don't have to check all 10. We have to check 4. Let's check the 4. So it's saying that whenever you add 2 vectors in the subspace, or subset rather, they have to also be in there. So if I added 1, 2 to -1, -2, the sum would be 0, 0, and that's already in there. And if I add 1, 2 to 0, 0, that's 1, 2, and that's already in there. And if I add 0, 0 to -1, -2, that's -1, -2, and that's already in there. So it looks like this subset is closed under vector addition. So there's 4 properties we have to check. Is it closed under vector addition? Is W closed under vector addition? And the answer is yes. Okay. What was one of the other 4 properties? Well, just looking on the list there, W has to have the 0 vector. The 0 vector is in there. And so 0, 0 is also an element of W. So that's true. We're checking off 2 of the 4 conditions are true. It's closed under vector addition, and 0, 0 is in there. Okay, so what more do we have to have? Each vector in W has an additive inverse in W. Okay, so here's a vector. 1, 2 is in W. Is its additive inverse in there? Its additive inverse would be what? -1, -2? Is that still a member of W? Answer, yes, because there it is, it's listed. So 1, 2, its additive inverse is in there. What about -1, -2? Is its additive inverse in there? So it's not good enough just to have the additive inverse of one element of W. You have to have the additive inverse of every element of W. Well, the additive inverse of -1, -2 is this one. So that's in there. There's only 3 elements in here. And 0, 0, its additive inverse is 0, 0 itself. So that's in there. So yes. So far, this looks pretty good. 3 of the 4 properties. It's closed under vector addition. It's got the 0 vector in there, and it's got its additive inverses in there. Does everyone see what I've checked so far?
Yes.
Okay, now the only condition that I didn't do is condition 2 is CX an element of W. So that's the last condition, is CX an element of W for what C? Whenever C is an F. Well, okay, so what could be an F? Let's take F to be the real line. Let that be the field you're working under, which is customary. And what could C be? Well, maybe C could be 2, for example. 2 is in the field. So is 2 times X in W for all X in W. Question, well, let's just let X be 1, 2. So suppose if X is 1, 2, what does this question ask? Is 2, 1, 2 an element of W? Well, 2, 1, 2 is what? How do you scalar multiply? You just multiply each component by the scalar. So that's 2, 4. So is 2, 4 in W? So what's in W? In W was only these 3 items. Is 2, 4 among them? No. This isn't 2, 4, nor is this, nor is this. So it looks like it's not closed under scalar multiplication, because if it were, 2, 4 would be in this. So the answer is no. And because it doesn't have these 4 conditions, what's the conclusion? The conclusion is W is not a subspace. In this example. Now be careful, subspace means more than being a subset, right? There's no doubt that W here is a subset of all the vectors in R2. It's just 3 such vectors. It's a subset. But to be a subspace is to be a subvector space, and that means really that W is a vector space by itself. It's just a generally smaller set than V, but if you just looked at a W by itself, it would satisfy all 10 conditions. Instead of checking all 10 conditions, what were the 4 conditions we had to check? So the 4 conditions to check were 4 conditions to check for what? For W, a subset of V, a vector space, to be a subspace, R instead of were. It should be closed under what? Vector addition? Should be closed under scalar multiplication. What else? 0 should be in there. So in this case, the 0 vector should be an element of W. These are the bullet items. And what's the last one? The additive inverse should be in there for every vector. So if X is an element of W, that's a vector, then minus X, the additive inverse, also has to be in there for all X. Well, not for all X in here. So I should say for this, yeah, I guess it's okay as I have it. If you have an X in W, then its additive inverse is also in there. Those are the 4 conditions you need to verify that W is a subspace. Okay. Questions on the example? Questions on the conditions? Because now the sort of problems that you could be asked and will be asked is someone will give you a subset of a vector space. And the question will be, is that subset a subspace? Which means, is it a vector space if you just consider the subset by itself? And the answer depends on the answer to these 4 points. If all four of these are yes, then the answer is yes, it's a subspace. If you only have 3 out of 4 or even fewer, then the answer is no. In this case, it was closed under vector addition. 0 was in there and it was closed. Whenever a vector was in there, its additive inverse was in there, but it was not closed under scalar multiplication. Therefore, in this example, W is not a subspace.
So 0 has to be in there for the additive identity, right?
Yeah, well, 0, I think that's an added yeah, 0, yeah, are you arguing that you maybe don't have to list this one? Is that what you're asking?
Well, I was just wondering like what the specific property was, I guess.
Well, I think simply it'd be easier just to go through the 4. So the requirement is that the 0, 0 has to be in the set. And you might be able, you might be able to say that that condition is met because it's closed under vector addition or closed under scalar multiplication, because 0 times any vector will be the 0 vector. So you might actually want to eliminate this condition, but I think it's probably simpler just to keep it as it is.
All right.
What can we learn from this? Well, let's stick with R2. This was just an example. One thing is, here's a further conclusion. When the vector space is R2 and W is a subset of R2, then for W to be a subspace of R2, we must have an infinite number of elements in W. So I'm saying that sort of comes out of this first example here. Now, in this first example, there were only 3 elements in W. But I'm saying, if I give you any W that has only a finite number of elements, that's not going to be a subspace. Why? Well, let me just give you a follow-up example. So for example, if W looks like 2 minus 1 minus 2, which is what I had before, 0, 0. But suppose I also had other stuff in there like 3, 5, minus 3, 5. It doesn't matter, but there's only just a finite number of these things. So maybe, it comes to an end. There's a last one. Maybe the last one, who knows what it is. It doesn't matter. So, but there's a last one here. I claim this won't be a subspace. Why? Well, this will not be a subspace, even though it's a subset, but W is not a subspace because it is not closed under scalar multiplication. For example, if 1, 2 is in here, then 2 times that would also have to be there. So if this is in W, and if it were a subspace, then what would follow? 2 times 1, 2 would have to be in there. But 2 times this is 2, 4. But not only would 2, 4 have to be in there, 3 times 1, 2 would also have to be in there. Not only 3 times this, but 4 times that would have to be in there. Because if it's closed under scalar multiplication, it means no matter what the scalar is, when you multiply this vector, which is in there, 1, 2 is in there, and the scalar multiplication would also have to be in there. Well, you can do this for any alpha. That would imply that alpha, 2 alpha would be in there. And what would alpha be? The alpha could be anything like 1, 2, 3, etc. So there would have to be an infinite number of vectors in here for it to be a subspace. Because why? Because we're assuming that alpha is in F, and we're assuming F is R. And if F is R, there's an infinite number of real numbers. So there's an infinite number of scalar multiples I can do for any vector that's in W, and they would be different. 3 times 1, 2 is not the same as 4 times 1, 2, and it's not the same as 5 times 1, 2, and so forth. So what I'm arguing is something that may not have been intuitive from the beginning. Any subspace, at least in R2, of R2 will have an infinite number of vectors. Okay. So if I knew that from the beginning, I could have gone up to my example up here and said, well, there's only 3 vectors in W, and any subspace of R2 will have to have an infinite number of vectors, and therefore this is not a subspace. Or said another way, the way that we actually did end up saying is it's not closed under vector addition, and because the scalar to be any one of an infinite number of vectors, this would have to have an infinite number of vectors in it. Now, by the way, if the vector field had only a finite number of elements in it, and I think I mentioned that the other day, it could be something like the integers mod 2 or mod 3. So if you're familiar with that, then this argument would not hold. But I'm just talking about the familiar calculus setting. In the calculus setting where you first learn vectors, you're in R2. So any subspace will have to have an infinite number of vectors in it. Any questions thus far?
I have a question, Professor.
Yeah, go for it.
So earlier you were talking about how technically every if a vector space is closed under scalar multiplication, then it has the zero vector. Is that what you said?
right?
So
Well, yeah,
yeah, so if like let's say we have a problem like on a test or a quiz or homework assignment, can we just say that? Like if it's closed under scalar multiplication, is that enough? Like for the answer, do we have to mention something else?
well, you'd have to go back over it and ask me the question again. What's the question? To prove something is a subspace? Is that
Yeah,
what you're
so
asking?
yes, so do we just say it has this? So how do we say it has a zero vector? We just say it because it's closed under scalar multiplication.
Well, in this case, it was pretty clear it had the zero vector because I included it, okay? In this case, well, I guess this case, I also included it, right? So in these two examples, the scalar vector was already there. So that meant that condition was met. But in this case, I'm trying to say that this cannot be a subspace. So really, it doesn't have anything to do about whether it has, if it didn't have the zero vector, then you could say no immediately. But it does have the zero vector, so that's not a way to rule this out as a subspace. The way to rule this out as a subspace is it's not closed under scalar multiplication. So just deciding the zero vector is not enough usually. I don't know if that's what you're asking, but I think that is. I mean, it has to have the zero.
That's not exactly what I was asking, but I think you still answered my question. So thank you.
Okay. I think it'll become clearer too as we do more of these. So okay. Let me give you another one. So how does R2 look? R2 looks like the plane, right? All vectors in R2 look like vectors in here, right? Suppose all vectors on the x-axis were in there. So suppose now, so W, were all the vectors that look like what? X comma 0, where X is greater than or equal to 0. Is W a subspace of R2? That's a question for anybody in the class. So if you can answer that, please do.
No.
Okay, who said no? Escar?
Yeah.
Antonio, sorry. Why not, Antonio?
Maybe because you can multiply the vector by a negative number, so you get like negative x0, and it's not in W.
So you're looking at scalar multiplication again. This would say, for example, that 1 0 is in here, right? And now I think what you're telling me is consider -1 times this, which would be what? -1 0? But this is not in there. Is that what I'm hearing?
Yeah.
Yep, you're right on the mark. Good job. So again, for W to be a subspace, it has to be a vector space. To be a vector space, it has to be closed under scalar multiplication. So he found a vector in here. 1 0 would be satisfy this condition. 1 is bigger than or equal to 0. So that vector is in there. But if you scalar multiply it by -1, you get this vector. So in terms of the picture, 1 0 would look like this vector. This is 1, and -1 0 would be this vector. And this guy isn't in there. Why? Well, everything in here has positive components, right? Well, positive first component at least. No, not even positive, non-negative first component. But if it's closed under scalar multiplication, then it would have a negative first component, and there's nothing here with a negative first component, so it's not closed. If it's not closed under scalar multiplication, it's not going to be a vector space itself. So the answer is no.
So if it satisfies the condition of vector addition and scalar multiplication, then it automatically satisfies the other two, right?
Not necessarily. Okay, so in this case, if you added two vectors in here, vector addition is closed. Vector addition is closed.
No, I mean, like if it satisfies both, like if it satisfies scalar multiplication and the vector addition, like if it satisfies both, then it also has a zero vector and it has an additive inverse automatically.
Not automatically. Let me show you why. Okay, so yeah, okay. Now, so you're trying to shorten the list. You can't get away with a shorter list. So I would still check all four, but let me show you why. Suppose W look like, well, let me see. So I'm trying to find something that's closed under scalar multiplication and vector addition. Well, I mean, you could have this. Suppose you had the set W that looked like all vectors x comma 0, where x is what? Positive, or x is what? Non-zero? So that means you would have all vectors that are going to the right, all vectors that are going to the left, but you don't have the zero vector. Let's see. Now, in this case, it would also. So what am I trying to say? I'm trying to say, I guess, if you added, yeah, I guess it wouldn't be closed under vector addition, right? Because you could do 1, 0 and add it to negative 1, 0. Both of them are in there. And for it to be closed under vector addition, in this case, that it already implies 0, 0s in here. So maybe you're right. Maybe if you have vector closed under addition and closed under scalar multiplication, what were the other two conditions?
Zero vector and the additive inverse.
Yeah, maybe you can get the other two automatically, maybe. At least in this case. But in general, I wouldn't risk it, okay? So if you're trying to show something's not a subspace, just show one of the four conditions is blown, is not correct. If you're trying to show that something is a subspace, there's only four conditions. I would just check all four of them. Don't try to make it a bit lighter work, because there could be some bizarre example that I'm not coming up with, where 3 out of the 4 work and the 4th one doesn't.
It's always easier to prove something isn't a subspace.
Yeah, yes, yeah, because there are 4 conditions, right? To be a subspace, there are 4 conditions. And the conditions are somewhat demanding. Closure is a demanding condition. So to have closure happening required that there'd be an infinite number of spaces, points in there, okay? Let me think and see if I can give you another example. So I guess I'd like to get to the main point. So the main point, what do subspaces of R2 look like? In general. Why? Because even though it's important to be able to verify or not verify those 4 conditions, I think even a better takeaway would be, how do subspaces in R2 look like in general? Does anyone want to try to answer that from the few examples we've worked so far today? Could you characterize how all subspaces look like in R2? So what do all subspaces of R2 look like? Well, okay. Let me try to answer that question with the little time I have left. Well, there's something called the trivial subspace. The trivial subspace is just, yeah, and actually this sort of contradicts what I said earlier, so it's a good thing I'm talking about it. The trivial subspace would just be the subspace that has only 0, 0 in it. Okay. Now, yeah, so I realize this does contradict what I said earlier. I said all subspaces have an infinite number of points in them. And this thing is actually a contradiction to that. So let's check that this, by the way, this is not the empty set, right? This is the set that only contains the 0 vector. So how many elements are in here? It contains one element. Contains one element. What element is that? It is the 0 element. So the third thing on our checklist is to be a subspace, you have to have the 0 vector in there. So this does that. Is it closed under vector addition? Sure, because the only thing in there is this. So if we're going to add it to anything, it's got to be itself. And whenever you add 0, 0 to 0, 0, you get back to what? 0, 0. So in a sort of trivial way, since there's only one thing in there, whenever you add it to itself, no matter how many times you add it to itself, you're only going to end up with 0, 0. So is it closed under vector addition? Yeah. What about scalar multiplication? If I take any real number and I multiply it by 0, 0, what do we get? 0, 0. Because 0 times 0 is alpha times 0 is always 0. So we're going through the checklist. It's closed under what? It's closed under vector addition. It's closed under scalar multiplication. Those two I sort of argued. 0, 0, the 0 vector's in there. The 0 vector is in W. And what's the last thing? All additive inverses are in there. But what's the additive inverse of any element in here? But the only element in there is 0, 0, and its additive inverse is itself. Because if you add 0, 0 to 0, 0, lo and behold, you do get 0, 0. So the additive inverse of everything in there is just the 0 vector. So all 4 conditions are sort of trivially satisfied. So I got to back off from my earlier statement. My earlier statement was all subspaces had an infinite number of points. Wrong. There's this guy, which is the trivial subspace, that has only one point, the 0 vector. Okay. So that's the smallest subspace I can think of. What is the largest subspace you can think of?
I was thinking maybe the vector xy such that x and y belong to the reals.
Yeah, which is the same as R2, right?
Yeah.
So the largest subspace would just be R2. Is R2 a subset of itself? Sure. Any set is a subset of itself. And is R2 a vector space? Yeah, you already know that. You don't even have to go through the properties because we know we've already said R2 is a vector space. So what do you got? On the smallest subspace, it's the trivial subspace, which only has a 0 vector. On the large side, the biggest subspace, it's everything in R2. But okay, those are the extremes. What's in between? Well, there are vector spaces in between that are not the trivial one and not the largest one. And what they look like would be vectors that along a line are along a line that passes through the origin. So what am I talking about? Well, I draw a picture. Here's the XY, here's R2. Look at the horizontal line that passes through the origin, which we normally think of as the x-axis. Any vector in that direction, be it to the right, be it to the left, or even if it has no direction, it's the zero vector. Any vector that's just like that, so what would that look like? It would be, W would be all vectors that have components x comma 0, such that what? X is a real number. So when x is positive, then you got a vector pointing to the right. When x is a negative number, you got a vector pointing to the left. When x is 0, you got the 0 vector. So I'm saying that all vectors you can make that are basically living on the x-axis would form a subspace. Why? I know I'm over time, but it's still important to emphasize why. The 0 vectors in there, if you add any two vectors in there, you're going to get another vector in there. Why? When you put the tail of one of those vectors to the head of the other, it's going to be still pointing in the x direction. Okay, so it's closed under vector addition. If you scalar multiply anything by any scalar you want, it's still going to be pointing in either to the right or to the left on the x-axis. So it's closed under scalar multiplication. It's closed under vector addition. The 0 vectors in there. And what's the remaining condition? Any vector has its additive inverse as well. So if you dream up of vectors like 2, 0, what is its additive inverse? -2, 0. And 2, 0 might be this guy, and -2, 0 might be this guy, and they're both in there. Okay. All right. So, but this is just an example. Another example would be vectors that are going along this way. So how would I write that? W would look like all vectors that look like 0y, such that y is an R. Same kind of argument, but I'm running out of time. But let me just complete the deal. What are the ones that I haven't done? Take any old line that passes through the x-axis. Pretend it goes through pretend it goes through the origin. That's what I need, right? So suppose it looks like this. Why don't we just do an easy one. The easy one would be the line that has slope 1, right? The line that has slope 1, how would W look like in that case? It would be all vectors, x comma y, such that what? X equals y. And they're both, x and y are both an R. So it would be vectors that go up this way, or this way, or this way, or this way. And it would be all such vectors like that. Can you argue that this is a subspace? I hope so. What you would have to argue is that if you added two vectors in here, you'll get another vector in there. But that's true, because if you add one this way to the other one going the other way, okay, I'll try to put it on top this way, you get the vector going like that, right? So if you add two vectors that are in the same direction, you're going to get another vector in the same direction. It should be on top of this line. So it's closed under vector addition. Scalar multiplication the same. If you just multiply a vector, what's in here? Any vector in here has the same coordinates. If you multiply by any alpha, you'll get another vector that has the same coordinates. So it's closed under scalar multiplication. The 0 vector in there? Sure. 0, 0 is in there. Additive inverses? Sure. Because if you wanted 2, 2, what would you have to add it to get the 0 vector? -2, -2, and both of these are in there. So I'm checking the 4 properties, all right? Why don't you verify it verify it in general. What's different than what I just did? Well, I did it on the x-axis and the y-axis, and I did it when y equals x. But I'm saying this would work for any old line you can dream up, as long as it passes through the origin. What if you had a line that doesn't pass through the origin? Is that a subspace? No. Why? 0, 0 is not on it. It's got to pass through the origin to make sure you've got the 0 vector in there, right? That's one of the 4 conditions. Okay, I'm out of time. Ran over. But let me go back and make sure I can cement some of these ideas. So, good. I did some homework. Let me give you a couple more. Excuse me.
Bless you.
No, thank you. Try number 8 on page 21. Page 21, number 8. And I can talk about it right now if you'd like. It's a little out in front of you, which means you probably might have to read the section a little bit. But on the other hand, I think it's relevant to what we're doing. I'm gone. I'm taking a 20-second water break just to take a break. And I'll be back in for the office session. And if I don't see you, have a good one. I'll see you next time. Oh, did you get the ad for the person who's interviewing? Did that come to you as did you get a colloquium notice or something in the mail?
I did.
Wonderful.
Yeah.
Yeah. So you're invited to come to that if you're. I think it probably would make more sense to come if you're interested in stat, since these people are giving their work in statistics. And I will be honest with you. Usually, sometimes if you go to a colloquium, you could be outside your depth in terms of what they're talking about, because these are new PhDs who are trying to tell us about their current research. So they're not necessarily trying to explain something that you've seen in your class yesterday. They're explaining something that you probably haven't seen. So I'm warning you that it may be maybe a little bit beyond what you know. But on the other hand, since they may be hired, and particularly if you're a stat person, you may actually have this person in your class. I think it might be a good idea just to come and see, which of the 4 people you like. Oh, by the way, I think it's down to 3 people now. I think one of them pulled out. So yeah, if you got the invitation for tomorrow, hopefully the Zoom link was on there too. And you could obviously just come for a little while and see if it makes sense to you. And if it doesn't, you can move on or stay as long as you like. Otherwise, I'll see you Wednesday. For those who can't stay right now.
Thank you, Professor.
See you next time. Okay, so that's my break. It's very short. Let me see if I'm doing this right. Actually, I think I'm not over time. I'm right, sort of on time, aren't I? Okay, I'm not used to being punctual. Questions about anything I talked about today or in the past? Any further explanations? Want me to go over this last example, for example? I mean, so at the end, we sort of came up with a nice conclusion. We're trying to visualize subspaces in R2. And the characterization that I came up with at the end is any vectors on a straight line that run through the origin will be a subspace. And anything else won't be. Well, I can't say that. What are the other ones? The other ones are the trivial ones. The zero vector by itself. So it just has one element in there. That's a subspace, but not a very useful one. And the other one is the whole space itself. Any questions about that? So let me double down on that for a second. So how would a possible test problem look on this material? So let me flip the page and give you one. So I will flip the page, I hope. Good. The lines on this. So here's a possible problem. That's problem. Suppose W looks like all the vectors that look like x, 2x, such that x is in R. Prove or disprove W is a subspace of, oh, I'm sorry, that was right. Is a subspace of R2. Okay. So, suppose this is simply stated. Now, we've been working with this, so we can probably do the problem in the context of what we just saw. But if you see it on the test and it's sort of coming out of left field, in other words, if you haven't been thinking about this material, what might you do? What you might do is graph some of the examples of this. So what would be in here? So for example, W would include, when x is 1, it would include 1, 2. When x is 2, it would include 2, 4. When x is 0, it would include 0, 0. When x is -1, it would include -1, -2. When x is -2, it would include -2, -4. So what I'm saying is, if you saw this problem, not right after class like what I'm doing now, but if you just see it later on a test and you haven't been thinking about the material, probably a good thing to do is to make a list of a few of the vectors that are in here. And if you did that, and you graphed them, 1, 2 would be a vector that goes from here to here. And of course, 0, 0 would just be the 0 vector. -1, -2 would be the vector that goes the opposite direction. But if I wanted to call this 1, 2, then I would be calling this vector what? Minus 1, 2. Minus 1, minus 2. And you can see that 2, 4 would be the same as this vector, just times 2, right? So what, even if you don't recognize this, if you just play around and list out a few of the vectors, what does it look like? It looks like vectors that are on this line here. And this line would be y equal to x, right? Because the second coordinate here, which is the y coordinate, is twice the first. So basically what I'm describing in this property are vectors that lie on this line. And this line is through the origin. So if you remember that subspaces of R2 include all lines that run through the origin. Now, by the way, the lines that run through the origin are called one-dimensional subspaces because they're lines, and lines are one-dimensional guys, right? So, which means this is true. This is going to be, what should we do? Whenever you got one question that occurs when you ever have a prove or disprove kind of thing is, which should you spend time doing? Should you spend time trying to prove it, or should you spend time trying to disprove it? And that could be confusing, and that could be time consuming, right? Especially on a test where time is sort of precious. So I'm saying that if you write out a couple vectors and realize that this description is really the same as being on a line through the origin, what should we do? We should try to prove it. Now, there's another little problem here. You might just say, well, I remember in class that any line through the origin is a subspace, so it's true. Well, that's great. That tells you that you should be able to prove it. But when I ask you to do prove or disprove, just recalling whether the thing is true or not is not enough. You need to give me an explanation. So now let's go through the explanation. The explanation would be what? We're going to try to prove it. And there's 4 properties we have to show. There are 4 properties to show. Because in order to prove that something is a subspace, we have to show. So what do we need to show? We need to see, or need to show, that W is a set which is what? Closed under vector addition. And what? Scalar multiplication. So I'm sort of grouping those together because they're both closure. What else do we need to show? Also need to show, or also need to see that the vector 0, 0 is in there. And we also need to see, we need to verify that if X, Y is in W, then what? Minus X minus Y is in W. We need to show that its additive inverse is also in there. So those are the four things we need to show that this thing would be a subspace. Okay, so to show it's closed under vector addition, take x1, y1 and in W, and x2, y2 in W. And what do we need to show? That if you add them together, that you get a new vector that's also in W. Okay, that's technically what closure means. If you have 2 vectors in W and you add them together, you want to show their sum is also in W. But in order to be in W, this condition meant that the second component is twice the first. So that means this guy really looks like x1 to x1. because that's what being in W means. The second component is twice the first. And there's an and in here. And this one means that x2, the second component is 2x2. And this is what by what? By definition of W. So I'm applying this as a real, real proof, right? And now when I add these guys together, what does the sum look like? But if I add x1 to x1 to x2 to x2, what do we get? Well, you add the first components and you add the second components. That's how you add vectors in R2. But you could rewrite this so that this is x1 plus x sub 1 plus x sub 2, 2 times x1 plus x2, right? That is, you can factor out the 2's here. And now by definition, this is in W. Why? Because the second component is twice the first, which is exactly the definition of being in W. This is just a way of describing a line, a particular line, right? Where the second component is twice the first. And this shows the technicality that if you added the two vectors that look like two vectors that are in W, since the second component is twice the first in each of them, you'll end up with a resultant vector which has the second component being twice the first, so it's still in W. So what does that show? That shows it's closed under vector addition. If that isn't clear to you, then that's something you got to work on, because that's actually proving something using the definitions, okay, and using what you're given. Let me move on to the next part. So this shows closure under what? Under vector addition. What else is there to show? Well, we got to show that it's also closed under scalar multiplication. So for scalar multiplication, I would put that under a separate argument. So a vector in W looks like x comma 2x. That's what things in W look like by definition. And if I multiply it by a scalar, call it alpha, what this looks like, how do you scalar multiply? It looks like alpha times x, comma, alpha times 2x. And if it helps, you can rewrite this as alpha x, comma, 2 alpha x. I put the 2 up front, because now I could see that this vector is in what? W. Why is this vector in W? Because the second component is twice the first. And that's the defining property of what it means to be in W. W has all vectors where the second component is twice the first. So I have to show that when I scalar multiply a vector that looks like this, I get another vector that is still defined in a way so that it takes place in W. So once in this part here is by definition of W. Why? Because W is defined up above to be all vectors where the second component is twice the first. And that's what this thing has. Okay, I'm going through this in detail, not to scare you, but well, maybe a little bit, scare you and prepare you for how the proof would work, right? Now, we're not done, but we're two-fourths done. What's the other thing? We have to show that zeros in here. But it's pretty clear that 0, 0 is the same as what? 0, 2 times 0. And that means, this is a product here, And that means this is in W. Again, by definition of W. Things in W have the second coordinate being twice the first. And 0, 0 can be thought of in that way, because 2 times 0 is still 0. Now you say, oh, that's tricky. Do I have to think of it that way? Yeah, because how do I know 0, 0 is in there? All you know about W is wrapped up in this definition here. That's all you're given about W. So you have to recognize that 0, 0 would still be in there because of this. 0, 0 still looks like 2 coordinates where the second one is twice the first. Okay, what's the last part? The last part would be showing that, show if X, Y is in W, then what? Its additive inverse is also in W. And show this is true. Its additive inverse is easy to come by. It's just the negative of what you had, right? Okay, so, but if X comma Y is in W, then what does that mean? Then X comma Y equals X comma 2X Y by definition of W. Because things in W have the second component being twice the first. And then, so what would that mean? Minus X minus Y would be just putting minuses in front of these things. Okay. And if you wanted to, you could write it this way. And if you write it this way, you can now see that the additive inverse has the form that you need to be in W. This is in W. Why? Because the second coordinate is twice the first. And that's how things in W are defined. So I need to show that its additive inverse is also in W. So I need to write its additive inverse. I know its additive inverse of XY would just be negative X minus Y, because I know if I add these two together, I get 0. But because we're talking about X, Y, and W, that means this second coordinate is twice the first. And then I write it this way so that I recognize that its additive inverse is in W. So that means I'm done. I've shown that its additive inverse is also in there. And that means conclusion. So W is a subspace of R2. Now, what is the frustration I'm trying to meet here? You could look at this and you can say, hey, it's a line through the origin at slope 2. And therefore it's a subspace. And you can say, well, Krennic proved that in class. Or at least he talked about it in class. So you can just say, why do I have to prove this since this is something that he actually did in class? Well, because I want you to know why it's true. I don't want you to just remember the fact. I mean, if I wanted that, I would just say true or false, is W subspace? And then you hopefully give me yes. And if I say explain, then you could just say Krennic said that any line through the origin is a subspace of R2, so I already know this. That's fine if it's true, false, and explain. But if it's not true, false, and explain, if it's actually prove or disprove, then you got to first figure out if it's true or not. In this case, I hope you remember what I said in class. But even if you remember, you have to go through, be able to go through the points of proving it, which this stuff is not immediate for many people, which is why I'm taking time to go over it now. Are there any questions about how the proof looks? It doesn't have to look exactly like this, but something like this, I think, would have to happen. Because, you know, you have to say there are 4 properties and I got to verify each of them. And somehow it has to go back to how W is defined. If you don't use that, there's no way to really prove it, okay? So questions on this problem?
I have a question, not specifically on this problem, but on the homework, the way the question is written, kind of gives you conditions for like V and asks, is it a vector space?
Sure, which one are you asking? Do you have a specific question in mind?
13 or 19.
Okay, let me
But
look at one.
they just ask you if it is a vector space and then they say justify. So
Uh-huh.
I know if you were to say no, you just need to show one of the things doesn't work, but for your
Right.
justification, would it be fine to just like say, yes, it is because it meets these 4 conditions and then just show the 4 conditions?
That would be great.
Okay.
Let me look to make sure I'm on the same page. So
Mhm.
literally, what page is that on? 13 on section 2, I guess?
Yes.
Let me make sure before I tell you one thing and then have to back off it. Section 13. Yeah, let V be all the ordered pairs. Okay, and define. Yes, so this doesn't deal with subspaces. This just deals with vector spaces itself, right? So
Mhm.
what they're asking is if you redefine vector addition not to be the customary vector addition, and you redefine scalar multiplication not to be the customary scalar multiplication, is it still a vector space for these operations?
Mhm.
And so, yes, I would say what you said is fine. But I'm trying to see, I don't think you can get away with 4 properties. I think you probably have to do all 10, right?
Okay.
Because the vector addition is redefined to be something different than the normal.
Okay, so on the 13, it redefines the addition property, but the scalar multiplication is the same. So would you just
No.
have to prove the rest of the addition ones?
Well, first of all, the scalar multiplication is not the same because you're not multiplying the second entry by C.
Oh, then I must have written that down wrong. Oops.
Yeah, so they're both different,
Okay.
but let's assume, and I don't know the answer, but I'm assuming this is probably not a vector space. So all you'd have to do is find one of the 10 conditions that don't hold.
Okay.
If you think, if I'm right, I mean, it's possible that they came up with some interesting weird definition where everything still holds, but I doubt it. This looks different enough to me that I don't think it is. You might want to check in the back, maybe see the answers there. But if I'm right, and this is no longer a vector space because the sum and the scalar multiplication are defined differently, then just find one of the properties that doesn't work.
Okay.
And if you can do that, then you don't have to worry about all of them, because to be a vector space, it has to satisfy all those 10 properties, right?
Mhm.
So if you go find one that doesn't work, then it's dead. Okay, it's not
Yeah.
what you want it to be. So
Okay.
that's how I would do or try to do it.
All right. And then 8 is looking at the subspaces. So that one would be fine, the 4 properties.
That's correct.
Okay.
Yeah, that's more in the newer section. That's correct.
Perfect. Thank you.
If you wanted me to do 13, I could or not. But I think you were pretty much asking just how to do it. And so
Yeah, I just wanted to make sure, like, if what I was going to put was sufficient or if I needed to do more. So,
okay. And now you're okay, I hope.
yes, thank you.
You're welcome. Let me play off this one that I just did. Suppose I tweak this one just slightly. how could I tweak it? Suppose I define W to be, well, okay, W prime. So it's a different W. And it's all vectors that look like this. So if I redefine W to be W prime, and the only difference is instead of the second component being twice the first, the second component is twice the first plus one. And then the rest could be the same. Prove or disprove W is a subspace of R2. Does anyone have an idea on how we would, or the direction we would proceed with W prime? So it's just a minor variation off of W, right? I just stuck
But
in
it-
the plus.
We could just disprove right, with the zero vector's not gonna be in it.
That would work fine, okay? Yeah, so if you wanted to, if you just saw this, and depending how much you remember, if you went through what I went through here to figure out whether to prove or disprove it first, you could try listing things. And I think you're right. I don't think there's anything you could get for X, because if X is 0, then Y has got to be 1, right? So you can't come up with a 0 vector. So if the 0 vector isn't in this set, then this would not be a subspace. Remember, a subspace is a vector space itself, but it's a vector space within an existing vector space. So it has to have the 0 vector, and you could simply say it doesn't have the 0 vector and you're done. Therefore, it's not a subspace. But if you didn't realize that, and you listed a few elements like I did here, I think what you'd realize, hopefully, would be that these are vectors on what? The picture is this. This is a vector on the line y equal 2x plus 1. So that's, I didn't draw it very well. It's a line that's got slope 2 and y-intercept 1. So it's rather steep. Somewhat slope of 2. And it doesn't go through the origin, and that's, okay, if it doesn't go through the origin, you don't have the 0 vector. So there's your answer. Is it a subspace? No. Why? Doesn't have the 0, 0 in it. So it doesn't have the additive identity. Or if you just remember from class that in order to be a subspace, it has to have coordinates that somehow correspond to a line through the origin, and this is not a line through the origin, that probably would be good enough as well to disprove it, because they're using something we proved in class to say why. Okay, so I'm just showing you that the same problem, just tweaked a little bit, the answer would be this is not a subspace, and there are different ways to come to that conclusion. You could realize that these are points on a line not through the origin. So it's sort of close, but close is not good enough. You have to have going through the origin. And if you really want to come down to it, I like what your answer was. It doesn't have 0, 0 in it, which is why you're restricted to lines through the origin in order to be a subspace to begin with. So I like your answer. But I also was saying, you know, say it again.
Instead, I think it fails the other property.
Yeah, it probably fails other properties as well. Is that what you're saying?
All the other.
I'm not sure it fails all the other ones. I'm thinking if you add 2 vectors on there, it looks like to me if you add 2 vectors on there, you've got another vector in the same direction.
It might be the same direction, but it's not actually, or I guess it wouldn't be the same direction because I did
No.
I did x equals 1, x equals 2 and added them together and you get 3, 8, which isn't actually.
Okay, okay. Yeah, so it looks like it fails that too. You're right. Yeah, because because you have to think of it this here. Let me draw the picture better. If we drew the picture a little better. So this is a line that's basically going, vectors that are on this. So there's a vector that looks like, yeah, I have to make sure I understand that. Let me think about it. Yeah, so maybe. Yeah, so if I have a vector for things in W now look like X, 2X plus 1, right? So if X is 1, it would look like 1, 3. And if X is 2, you can get something like what? 2, 5. And if you added these two vectors together, you get 3, 8. And that's not equal to X. I don't think so. No, that's not something that looks like X, comma what? 2X plus 1. Because if that were true, then X would have to be 3. And 2 times 3 is plus 1 is 7, not this. So if you add two vectors like this, you're right. You don't get a vector that has the same form. So it's not closed even under vector addition. So that would be another way to disprove it. Yeah. I'm trying to see, is it closed under scalar multiplication? I don't think so again, right? So maybe none of the properties hold, okay. Anyway, so there may be many ways you can show that this is not a subspace. Okay. That's all I was trying to do to wrap up. Any questions you have? Homework? Anything else I said in class? Any other questions at all?
Professor, I guess I have a general question about
Sure.
the last homework assignment. I submitted it last Friday, but I didn't have my name on it, so I just resubmitted it again today. Is that fine, or is that going to count as late now since I have to add my name onto it? Or
as long as I see your assignment there with your name, then you're going to get credit for it, okay? Because then I can recognize who did the homework. Yeah, the one that has no name on it last time that I saw, clearly I wouldn't know who submitted it, so I'll have to sort of not worry about that one. But I'm glad you resubmitted it, okay, which is why I mentioned it in class to begin with. So you should be fine.
okay, all right, thank you.
I'm presuming it's going to show up there with your name. Okay. If it doesn't for some reason, then I'll have to get back to you.
Okay, thank you.
We got it. Other questions, math or otherwise? Would you like me to do one of your homework problems?
Sure.
Which one?
19.
19. Okay, that's on page 16, right? Am I doing the right one? Or is in section 2? Yes, no?
Yeah, it is. Thank you.
Okay,
Yes.
okay, great. So let's clear the deck. Let's add a page. Let's put some lines on it if we can. And let's look at what 19 is about. So 19 says, you've got vectors in R2 to first begin with. So it starts off with telling you that the vector space are vectors that look like A1, A2, such that, that's hard to read the colon, such that A1, comma, A2 are both real numbers. Okay, so that's the usual vectors in R2. Define addition of elements of vectors coordinate-wise. So addition is defined the same way as normal. So if I wanted to, I would take A1, comma, A2, and I'd have B1, comma, B2. Addition would be just what we expect, A1 plus B1, comma, A2 plus B2. That's what they say, define addition coordinate-wise. And for vectors in V and C a real number, define the scalar product differently. Okay, so the scalar product is different. The scalar product is defined this way. So if you take C as some scalar, and you want to multiply it by the vector A1, A2, what you get depends on something. You'll get 0, 0 when what? When C is 0. But when C is not 0, you'll get something different. You'll get C A1, comma, A2 over C. Okay. Question. Is V a vector space over R with these operations? Justify your answer. And V is this. V is the usual. Okay, so to be a vector space, there were what, 10 different properties? 5 of them had to do with what, vector addition? And 5 of them had to do with scalar multiplication. Since vector addition is defined in the usual way, I think the 5 properties with vector addition are still going to hold. Namely, if you add 2 vectors together, you're going to get another vector in R2. That is, closure will hold. The commutative property should hold because the addition is the same way as it was before, and it held there. The associative property should hold. What are the other 2? The other 2 is that there's an identity, which would still be 0, 0, I think. Yeah, because if you add 0, any vector to 0, 0, you still get the vector. And the additive inverses would still be what they were. So I think all of this is okay because it doesn't involve scalar multiplication. It just involves vector addition, and vector addition is defined in the customary way. So what we'd have to concentrate on are what about the 5 properties to do with scalar multiplication? Okay. So the first property would be closure, perhaps. So we're trying to show that if we multiply vector A1, A2, do we always get a vector in R2? Well, let's think about it. If C is 0, then you get the vector. Well, so if C is 0, that would be alpha being 0. So if alpha is 0, then you get 0, 0 for this thing when alpha is 0. And that's in R2. But if alpha is not 0, then what do you get? Then you get alpha A1, comma, A2 over alpha. And if alpha is not 0, this is well defined. And so is this, and this will be some other vector in R2. So I think closure is okay. I'm saying that if you multiply any vector by any alpha, if alpha is 0, you get a vector that's in R2, and if alpha isn't 0, you get another vector which is also in R2. So closure is fine. What's the next property after closure? I think, well, let me just take them in the, I could just take them in their order. So let's go back and look at this, look at the properties. They're on page 7. So we've just done the closure one. The next one would be the associativity property. So if I'm on page 7 now, just looking at the properties. Maybe I'll go over to their notation. So the notation there, I'd have to show that if A and B were real numbers, and if I take A, B as the scalar multiple of some vector x, so x is a vector in R2, that we would get the same thing as A parentheses Bx. That's what's listed in the book as property scalar vector space property 6. Excuse me. So let's check that one, if it works. I think there are 2 cases to go on, because the scalar multiplication property depends upon whether the scalar is 0 or not. So case 1 might be when AB is 0. When AB is 0, then, well, if AB is 0, how is that true? This has subcases. This means either A is 0 or B is 0 or both. So let's just say case 1A, A is 0 and B is not. And case 1B, A is not 0 and B is. But let's just do case 1A first of all. So if A is 0 and B is not, then the product is. And in that case, the product here would be 0. And then back on how this is defined, when the scalar is 0, we would just get on the left side, we would get what? 0, 0. So I'm looking at case 1A. I'm looking at the case when A is 0 and B is not. Then in that case, the product is 0. In that case, I'm up here. Now, what's going on the right? On the right side, so is that equal to? That's the question. So we're trying to see if this property holds. If we did B times X, B is not 0. So when we do B times X, we're going to get this expression. Let's assume that X looks like what? X1, X2. Okay, so then B times that would be what you have over here. Okay, so that would be Bx1, and you'd have what? X2 over B. And that all makes sense because B is not 0. So that's what this is. But over here, A is 0. And when A is 0, then this whole thing just becomes 0, 0. Which means you get equality. So it looks like in that case, you're okay. Does it matter if this is reversed? I don't know. If A is not 0, but B is, if B is 0, then you'd have on the left side, you still have this. And on the left side, you still have B times the vector this, but B is 0. So that would give you the vector 0, 0. So checking this in case, I'm doing this case now. And I have A 0, 0. And if A is non-zero, then I'm back over here. So I'd have 0 over, or 0 times A, 0. And in this case, I would have 0 over A. And they're both still 0, 0, right? So it looks to me in either this case or this case, I'm getting this thing to work because I'm getting 0, 0 on both sides. Now, what about if they were both 0? If they were both 0, which is possible, then this side again would be 0, 0, according to this. And I think you would get 0, 0 over here as well. So it looks like this works. In every case that I can imagine over here, let me see. Well, am I doing every case imaginable? I guess I didn't do the case when we're trying to verify this for all A and B. What about when A and B are not 0? Does everything work? When A and B are not 0, what do you get over here? You would get, just replace C by A times B. So it would be x1 times A times B. And you would get what? X2 divided by A times B. So A and B are both non-zero, and I'm just checking this property as well. It looks like I'm getting this. And if I do them step at a time, what do I get? I don't know. Step at a time here, I'd first do B, so I'd have X times B. X1 times B, I believe, yes. And then I would have X2 divided by B. So that's what happens if I do B first. And then if I multiply, scalar multiply by A afterwards, what would that give me? That would give me, by this definition, it would give me AB X1, and it would give me what? This thing, X2 over B, divided by what? Divided by B. See if I'm doing that right. No, divided by A. Okay, so are these the same? A, B, x1, yes. A, x2 over B, yes. So I don't see anything wrong with this property. Okay. So what's next? Try VS7. So what does VS7 say? Vector space 7 property. It says if you multiply A times X plus Y, it's one of the distributed properties, you get AX plus AY. And that has to happen for every A and F and for every X and Y and B. Okay. So testing that out. If A is 0, that's one case in the scalar. So we're going back to this. A basically would be the C here, and this would be, well, let's just write it out a little more. So this is A, and this would be, say, x1, x2 plus y1, y2 equal A, x1, x2 plus A, y1, y2. So that's what this property is saying. If A is 0, the scalar multiple is just there, 0, 0. So in that case, if A is 0, this is 0, 0, each of these are 0, 0, and it works. So A equals 0 works. You get equality. What if A is not 0? If A is not 0, let's just do each of these first. A x1 so it's this thing. So it would be A x1 for this. And then it would be comma x2 divided by A. That's what this thing would be. And this one would be what? A y1, comma, y2 divided by A. We're assuming here that A is non-zero. And this one over here, well, here we would do the sum first. So it would be A x1 plus y1, comma, x2 plus y2. And this is the point in question. Is this the same? Well, if A is non-zero, that's what we're assuming, then this one would be what? Would be x1 plus y1 over A. And the other one would be x2 plus y2 over A. And so it would be asking, is this vector equal to this one?
Professor,
Yeah, please.
on the first term, it'll be 8 times x1 plus y1.
This one here, yes.
Under that one.
Uh-huh.
Shouldn't be 8 times the quantity of x1 plus y1.
You're absolutely right. Thank you. Because I have to go back up here to see how the scalar multiplication works. So you're right. It should be 8 times that. Thank you. So let me alter this slightly. Everyone see how the correction is correct, and I appreciate it. Because I have to apply the scalar multiplication as given up here. When the scalar is non-zero. So I just multiply the first component by the scalar and I divide the second component by the scalar. And I wasn't doing that. So this is what we got. And so now if we compare this, you get ax1 plus ay1. And if you add these two together, you'll get ax1 plus ay1. So the first components seem to be correct. What about the second components? This one is x2 over a plus y2 over a. That seems to work as well. Common denominator is a, so you would just add the top. So this looks fine. Okay, so far so good. It's sort of, point by point, but hey, that's how it is. What's next? Well, vector space condition 8. Okay, so this last condition asks if you have a plus b times a vector x, is that equal to ax plus bx? So it's a distributed property this way where you're sort of distributing the x's times the scalar. Okay. So it seems to be the last one to check. Why don't we assume, first of all, well, we have to see. Well, I don't know. Let's just go through it, I guess, in the order. So assume a plus b is 0. And let's assume a little more. I mean, there's different ways this sum could be 0, but let's just also assume that b is minus a. Okay. So if b is minus a, what does all this become? Well, this would become this would just be 0 up front, right? So in that case, scalar multiple 0 times a vector, our definition tells us that if c is 0, then you just get 0, 0. So this left side would be 0, 0. Under this assumption. And I'm going to assume that that a and b are not 0. Okay, so if a and b are not 0, then I have a different thing to do over here, because now I've got a and b not 0 times x. What does that tell me to do? It tells me to use this part of the definition. So I would have, and let me assume that x is as before, x1, y, x1, x2. So what would this look like? It would look like what? A x1, comma, x2 over a. And this one would be what? Similar. B, let me make sure I'm doing this right, but should this, yeah, I guess that's right. B x1, comma, x2 over b. And before checking that, I want to make sure that I did this correctly. So the scalar multiplication, when the scalar is non-zero, is just the scalar times the first entry, and then the second entry divided by the scalar. So I think these are both correct. And so now are these equal? I don't know. So if I just add these together, I would have ax1 plus bx. What was this x1 again? Yes. bx1, comma, x2 over a plus x2 over b. Okay. And you could factor out the x1 and you'd have a plus b, but we assumed a plus b is 0, so that seems fine. And what gives here? Let me see, you can factor out the x2 and you'd have 1 over a plus 1 over b. But what do you know about b? B is minus a. So if b is minus a, what would this be? It would be x1 over a minus 1 over a as well. Now, I guess it comes down to what do I know? Interesting. What do I know here? If a is non-zero, which is what I assumed here, then you would have 0, 0, which is what you want. On the other hand, suppose a and b would both be 0. Well, if a is 0, then this doesn't even make sense. So I have to think about that one a little more. So it could be that a and b are both 0. In that case, the sum is 0 and the left side is what it is. That part's fine. So I'm sort of doing a separate case. I'm looking at the case when a equals b equals 0. When a equals b equals 0, this one and a and b equals 0, I just get 0 zeros for this, right? So if my scalar is 0, I just get 0 zeros. So I use a different thing. And so I'm not using this, and I'd have 0, 0, and I'd have 0, 0. So this seems to work as well. I'm not seeing where it goes wrong. Unless I overlooked a case where that does go wrong. I don't see it. Did someone, well, okay, so I think I've gone through all the properties that I'm supposed to go through. And I think I verified them. Now it's a little tricky because when you do the scalar multiplication up here, it's got these two conditions, right? Depending whether the scalar is 0 or not. When the scalar is 0, it's easier. Excuse me. It's easier in that case, but when the scalar is non-zero, then it has this form. So you really have to do both cases as you proceed, but I don't see an issue. What did they say? I'm curious. Oh, also I have to be careful. I have to run off in a couple minutes. Let me see. So this problem was what, 19? I mean, if nothing else, you're seeing at least the approach. Let's see what they say in the back. Curious. If it's wrong, then there's just a case I overlooked. But I don't see it. I don't see it being wrong.
Well, is it safe to assume that a plus b is equal to 0?
Well, no, you have to assume all these cases, actually. So, I mean, you have to try, because it has to be true no matter what A and B are, right? So if I didn't cover a case where it goes wrong, then that's on me. Let's see. So this is in section what, 1, 2, 19, no, they don't say. Unfortunately. Okay, so I'll leave it at this since I have to run, unfortunately. But the process is correct. You have to methodically go through each of the conditions to see if they work. And it's complicated because the scalar multiplication has two cases, depending whether the scalar is a 0 or not. So you'd have to check it in all eventualities. And over here in the later cases, you've got two scalars. So it could be that I didn't check all the cases, but the cases that I did have time to do, it looked like it was working. So I guess I'll leave it to you to check it more carefully, but do you understand it? Do you understand at least the process? This is what you have to do. And actually it's not, it could be worse because there could be all 10 conditions to check. It only is the ones involving scalar multiplication because vector addition is still the same. But this is what's involved. If you get some, you know, I mean, the obvious question is, how did anyone come up with this definition of scalar multiplication? So I won't say this one's closed because I won't be shocked if maybe I overlooked one case because it seemed like down here I was assuming this. Maybe if I assume if these are, well, all these cases have to be considered. The sum is 0. One may be the negative of the other. They both could be non-zero, or maybe they're both 0. And then I'd have to go through this a case. I think what I didn't do is go through this when A and B is not 0. And so when A and B is not 0, I think that probably should be done. I'm tempted to do it, but I got to go somewhere. So try that case. Here's what I suggest. This is still homework. Try the case when what? A plus B is non-zero. Okay. Now, when A plus B is non-zero, it still could happen. For instance, like this could be 0 and this could be 2, right? So there's these kind of cases. I would alert you to that. Check those as well, because I think my work here is incomplete. Sorry, I don't have a little more time, but I hope it helps. I gotta go. I gotta go to this other meeting. Good question, though. I think hopefully you got the idea. To be honest with you, I'd be surprised if this works, but so far it is. As far as I've heard it, so far it's working. So I would urge you to check this last case for the last property. All right, later. Take care.
Thank you, Professor.
Yeah.